This video is going to cover the last new topic for the semester, contingency tables or tests of independence. We're going to do a hypothesis test that two criteria are independent of each other. So let's go look at the document. Okay. Suppose that we go to a political rally of sorts or a meeting, political meeting of sorts, and we find 300 people there. And from each person, we obtain their political affiliation, which may be Democrat, Republican, or Independent. And at the same time, from each person, we determine whether that person is male or female. So we've got 6 possible situations here. We've got male Democrats, male Republicans, male Independents, female Democrats, female Republicans, or female Independents. So each person has 2 criteria associated with them. And we're interested in if these 2 criteria, whether what political affiliation they are and what gender they are, if those 2 things are independent of each other or related somehow, dependent or related. So if they're independent, we would expect that the proportion of Democrats who are male would be about the same as a proportion of Republicans who are male. And that would also be about the same as the proportion of independents who are male. If they were dependent or related somehow, then there's something causing those proportions to be different. In other words, among the 3, looking just at the male proportions of each of the political affiliations, we would, if they are related, then those proportions would be different. So say, let's say that when they were independent, that those proportions were about 50%. So 50%, if they are independent, 50% of Democrats were male, 50% of Republicans are male, 50% of independents are male. But when we look at a group of people where the relationship between gender and political affiliation is dependent or related, then we might see something like 50% of the Democrats were male, but 75% of the Republicans were male, and maybe 60% of the independents were male. The proportions of each of those that were male would be different. And then and I've got some examples here. Suppose that we have 300 people, and it turns out that 70 of them are Democrats and males, 87 are Republicans and males, and 18 are independent or male. And Democrats, 50%, or not 50%, but 50 of the Democrats were female, 63 of the Republicans were female, and 12 of the independents were female. So if the political affiliation and the gender were independent of each other, we would expect that the proportion of the Democrats, there are 120 Democrats, that the proportion of the Democrats would, who are male, would be about the same as the proportion of Republicans who are male, and the proportion of independents who are male. So the proportion of Democrats who are male would be 70 divided by the total of the Democrats, 70 over 120, and that turns out to be about 0.583. For Republicans, we take the proportion, the number of male Republicans, and divide by the total number of Republicans, and we get about, we get 0.580, very close to 0.583. And then for independents, we have 18 independents who are male out of the 30 independents. And that turns out to be a proportion of males equal to 60% or 0.60. Again, fairly close to the 0.58 and the 0.583. And if this were the case, we would suspect that there is no relationship between political affiliation and gender, and therefore they are independent of each other. Now, if we have this situation where we have 300 people, and again, we have 70 Democratic males, 50 Democratic females, but we have 65 Republican males and 85 Republican females, and independents are 18 male and 12 female. And we see that the Republican numbers are changed from the previous table. Now, if we find the proportion of each of the political affiliations that are male, we're going to see that those proportions are different. So for Democrats, 70 out of the 120 are male. Again, that's 0.583. But 65 out of the 150 are of the Republicans are male. That is only 0.433. And for independents, the numbers are the same. 18 out of 30 males, Republican males. And that again is 0.600. But we see that 0.600 and 0.583 are very close together, but we have Republicans who the proportion of Republicans who are males is significantly lower. Well, is it significant? We're not sure, but it appears to be. So if we just observe what we have in the table, what the proportions are for each column, pick one of the values in the column, like male, and look at the proportion of each of these that are male by taking the number that are of the political affiliation that are male divided by the total number of the political affiliation. And comparing those, we can get an idea of whether we think that these two criteria, political affiliation and gender, are independent, like this set right here, or not, like this set right here. But now what we're going to have to do is formalize a hypothesis test that we can use to make decisions about whether we think they are independent or not. So the structure of our hypothesis test it's called a chi-squared test. And we're going to be using the chi-squared test on the calculator. This is not to be confused with the test of standard deviation. That's a chi-squared test statistic, but this is not the test for that. This chi-squared test on the calculator is a test of independence. It's a contingency table test. In these tests, our claim is going to be that the two categories or criteria are independent, which means that they're not related. The null hypothesis will be the same as the claim. The two categories are independent, not related. And this is always going to be the case in all of our tests of contingency tables or tests of independence. H1 will be that the two categories are dependent or related. This is the alternate to the null. The null is independent, not related, and the alternate is dependent, related. Okay? So our test statistic, and you will not have to know this, it's a chi-squared test statistic, obviously, because we're calling this a chi-squared test of independence. It looks like this. I'll briefly discuss it, but you will not have to know what the formula is here. But basically, the test is looking at what was observed, what was in the original matrix here, the rows and columns that make up the table, not including the totals. You do not include the totals here, okay? You're only looking at the 6 numbers that give you a combination of one of the criteria, of both of the criteria, okay? Or both of the categories. Okay. And then we would, if they are independent, E would be the number that we would expect in each one of those cells. We find that difference and we square it and we divide by the expected number as well. And then we add those up. So we have 6 different values in here that make up the 300. And for each one of those, we would take the observed value and subtract what is expected, square it, divide it by the expected number, and then add those up for all 6 of the cells. And once we have that, that is our chi-squared test statistic. And this is a right-tailed test, which, and so we will only reject if the chi-squared test statistic is large enough, farther from the mean, to the right, okay? Now, we're going to use, like I said, the test on the calculator, the chi-squared test on the calculator, and like all of the hypothesis tests that we do, it's going to give us a test statistic. It's going to give us the value of the chi-squared test statistic. And it's going to give us a p-value, which we will compare to the significance level alpha. And if it is less than, if the p-value is less than or equal to alpha, we're going to reject H0 and say that the 2 categories are dependent or related. If it is greater than the significance level alpha, we're going to say that the 2 categories are independent or not related. So fail to reject, H0 is what we're going to say. Reject, H1 is what we're going to say. You need to remember those 2, okay? Fail to reject, we're going to not support, but we're going to basically not be able to reject independence. If we reject, we're going to reject independence and say that they are dependent or related. Okay, so we get the test statistic from the calculator, we get the p-value from the calculator, and we make our decision using the p-value approach, and we state our conclusion as I indicated, okay? So let's look at our 2 particular problems here. The one where we're going to start out with this table on the left, which is this table here. We're going to use a 0.05 significance level. And we're going to say in the claim that the gender and political affiliation are independent or not related. We'll say in the null, the gender and political affiliations are independent or not related. And if the alternate is going to be that the gender and political affiliation are dependent or related. The test statistic from the chi-squared test is chi-squared equals 0.041. The p-value from the chi-squared test is going to be 0.9796. And obviously that is greater than 0.05. So we're going to fail to reject H0. And we're going to say that the 2 criteria are independent or unrelated. There's not sufficient evidence to warrant rejection of the claim of independence. Okay. Now, how do we do this? How do we use this chi-squared test? Well, you're going to put the data from the table, these 6 values right here, not the totals, just these 6 values that we have for each combination of a category level or criteria level for each of the categories. So Democrat and male, we're going to put the 70 into the calculator. We'll put the 87 in, et cetera, up to the 12. Okay. Where does that go? Okay. It goes into a matrix. We have not seen matrices before. A matrix or matrices, which is plural. So let's look at how we're going to do that. We're going to do second, press the second key and the x inverse key, x minus 1, x to the minus 1 power. Basically, it's 1 over x, but that key as it's expressed right here. And we'll see where that takes us. And so here's what we're going to do. I'm going to go look at the calculator and we'll put the data in. Let's clear out of here. Second quit. Okay, clear. All right, so we can't run the chi-squared test until the data's into the calculator. So let's put the data in. First thing we're going to do is go, you'll see above this x minus 1 key, it says matrix. That's where we need to get to. So I got to do second x minus 1. And it takes us to the matrices. There are 10 of them, starting with A to B, and they are in the square brackets. That tells you that it's a matrix. And what we're going to do, we're going to use A as our data. We're going to put our data into A. So let's go over to edit. So the first thing you're going to do is go to the matrices. That's that second x minus 1 key, and then right arrow to edit, and then hit enter. And it's going to tell us that we're going to edit matrix A. The two numbers here at the top to the right of the name of the matrix are the number of rows and the number of columns. We had in our data 2 rows indicated by male and female. We had 3 columns indicated by Democrat, Republican, Independent. So we need to type in 2 and enter, and it takes us over to the next one. And then 3, 2 rows and 3 columns, and enter. And now it gives us those 2 rows and 3 columns, and now we're ready to put the numbers in. Okay, the numbers we had going row by row were 70, 87, 18, and then in the second row, 50, 63, and 12. Okay, now our data is in a matrix. You need to remember where to go to get to matrices. Second, x minus 1 key. Then you're going to enter the number of rows, enter, hit the enter key, number of columns, hit the enter key. The first row, the first number in the first row, enter. Second number in the first row, enter. And keep going that way, row by row, until you're done putting all the data into those 2 rows and 3 columns. And then you're going to get out of there. Second mode. Our matrix is set up. The data is in the computer or calculator. Now what we're going to do is run the chi-squared test. And where are all the tests? They are in second, stat, over to tests, and down to the chi-squared test. Okay, and hit enter. Observed has to be A. And if we wanted to, if we didn't have anything in there, typically the first time you do this, you'll see A for observed and matrix B for expected. You don't have to worry about what's in matrix B. You don't have to worry about setting up matrix B. Whatever matrix you put in for expected, the calculator will automatically set that up. And it's just basically going to use it as a placeholder. It will calculate all the expected values and then use the A and B matrices to come up with the test statistic using that test statistic formula. So let's, just in case you need to change one of these, let's say we wanted to change, if the expected was another matrix instead of B, we would do second X inverse or X minus 1. And we would say we wanted to make it C. We would go down to C and hit enter. And now C is there. But I would like for you to use B, A and B consistently. That way you never have to change this. You only have to set up your data every time you run it in matrix A. So let's change this back to B, second, X minus 1, down to B, 2, and enter. And then now we're going to go down to calculate. And there's our test statistic, 0.041 to 3 decimal places, and 0.9796 is the p-value to 4 decimal places. So let's go back and make sure that that is our value in the document. And I believe it is exactly what we thought. And so we would compare the p-value to alpha and determine that we're going to fail to reject because the p-value is bigger than alpha. And then so we can't reject H0. So basically we're saying that the 2 criteria or categories are independent. Okay. And as you recall, when we looked at these numbers early at the very beginning of this video, we found that the proportion of each political affiliation that was male was about the same. And so we kind of guessed that these 2 criteria were independent. Now let's look at the same problem, the same test for that second matrix. Again, we need to set up the test or data into matrix A. So these numbers right here have to go into matrix A. Our claim is still going to be the same. Our H0 is still going to be the same. Our H1 is going to be the same. Claim is always going to be that the two categories are independent or not related. Null hypothesis is going to be the same as the claim. The 2 categories or criteria are independent and thus not related. And then H1, the alternate hypothesis, is going to be that the 2 criteria or categories are dependent. They are related. Okay. So let's go ahead and put those numbers into matrix A and run the chi-squared test for this. So let's come back and look at the calculator. Let me clear this screen. Where are we going to go find? We got to put the data into the matrix. So we need to go second, X minus 1, over to edit. And we need to set up and then hit enter because we're going to use matrix A again. I'm just going to, I have 2 rows and 3 columns again, so I'm just going to hit enter, enter, and now I'm going to put the numbers in. 70 was the same in the second matrix, or second table as well. But Republican was 65 Republican males, and 18 was correct, same, enter. 50 was the same, enter. And now this was 85, enter. And 12 was the same, enter. Okay, so we're done with, oops, didn't want to do that. We're done with the matrices. Let me make sure I get this correct. I'll put the 12 in there again and hit enter. Okay, so to get out of here, we don't want to change anything else now. We've got the data that we're given in the table in matrix A. So let's do second mode to quit out of there. And then we're going stat, right arrow to tests, down to chi-square test, or I could go up. It may be closer to, faster to go up to the chi-square test, and hit enter. A for the observed values, B for the expected values, and we calculate, and we get a chi-squared value of 7.083 and a p-value of 0.0790 to 4 decimal places, rounded to 4. And then I'm going to let's get out of here. I'm going to stop sharing and come back to the document. And 7.083 for the test statistic, and the p-value is 0.0290. And since 0.0290, and we're doing at the 0.05 level again, since 0.0290 is less than 0.05, we're going to reject H0 and say there is significant, I'm sorry, the two criteria are dependent or related, okay? There's sufficient evidence to warrant rejection of the claim of independence. And for both of these tests, the sample tests in this document, I've shown you step by step what we're doing here. So it should be fairly clear, and you should be able to use these demonstrations here as directions to do this on other tests. Okay, now last thing we want to worry about is assessing if we reject, how are we going to assess this relationship? Well, you'll remember what we did in the first one. We assumed that they were going to be independent, and the test said, yes, indeed, they are independent. And when we looked originally at the proportion of males in each of the political affiliations, we saw that that was about the same across all political affiliations. So what we guessed was going to happen did happen. But in the second one, we looked at those proportions and we guessed that we're probably going to say they're dependent because the proportions were not the same. So indeed, that's what happened in the test. So really, that observation of the proportions of each affiliation that were males gives us an indication of what the relationship is. It appears that, at least in this example, that there is a disproportionately small proportion of male Republicans than the other political affiliations. Okay, the proportion the Republicans have a lower proportion of males, and that would be our discussion of the relationship that caused us to reject. Okay, We rejected 8-0 because the distribution of gender was different for Republicans. In particular, we would say that a significantly larger proportion of Republicans are females compared to other parties, or a significantly lower proportion of Republicans are males compared to other parties. That would be what we would say regarding why we ended up rejecting. And that concludes this discussion of tests of independence or tests of contingency tables. Okay, let's, and like I said, this is the last topic. So you should be good to finish the last homework and quiz for chapter 11.